Okay, recording started. Then let me share my screen. Okay, is it visible? Is my screen visible to everybody?
Yes, sir.
Yes, sir.
Okay, good. Okay, so today's topic is about set sizes. Of course, the size, that word size is not perhaps fully mathematical, because mathematicians use other terms like cardinality to denote whatever we call the size of sets. Anyway, whatever name we give to the concepts, that's not a very important issue. So countability and uncountability constitute a topic starting from, I would say, early 20th century or late 19th century. And these things are conceptually so far the most sophisticated in these courses. Okay. So you will have some trouble in grasping all the concepts initially, but with some practice, I hope you will eventually start understanding the nuances and the basic implications of this size kind of arguments. To that effect, let us look at some exercises with the hope that this will broaden your understanding. So I start with this. Okay, first of all, let me go to the chat section. Okay. Okay. So first of all, this is our first exercise. Suppose that A and B are two uncountable sets, such that A is contained in B. Prove or disprove A and B are equinumerous. So the logic behind this, behind setting this question, is that we have seen that all countable sets are essentially of the same size. Size is again within quotes, whatever you call size. But what about uncountable sets? Any two uncountable sets have the same size, same cardinality? And this question is asked in this exercise. Moreover, you should specify this A and B in such a way that A should be a subset of B. Yeah, so think for a minute and give me an answer.
Sir, is it wrong?
Is it wrong? What is your intuition behind saying this is wrong?
Sir, I thought that the subset all power set of real numbers, and I found an example that if we map every set to every real number, then we get a subset of the power set which is of cardinality LF, and which is a subset of power set of real numbers. But power set of real numbers has cardinality more than that, so it is wrong.
So this is wrong. Okay, so good. So, okay. Maybe this is. So, by the power set theorem, which is a very powerful theorem, R is of size strictly smaller than the power set of R. Okay. But I know that R is already uncountable, and I have defined a set which is of size bigger than the size of this. Both are infinity, both are uncountable infinity. So multiple uncountable infinities are there. So this is our first understanding. Okay. So there is actually a hierarchy of uncountable infinities. For example, 2 to the power 2 to the power r, sets of real numbers. So that is 2 to the power 2 to the power r. That is again strictly bigger than the size of 2 power r by the power set theorem again. So there is actually a hierarchy of uncountable infinities. Of course, you may ask the question, are these all the uncountable infinities? But this is a difficult question, so let us not raise this issue in this so-called simple-minded discussion. In any case, so I take this as 2 power r as b. So shall I take a as r? Is it a good thing?
No, sir.
Because elements of r are individual real numbers, whereas elements of b are sets of real numbers. So this extra condition, a contained in b, is not satisfied. So what I do, I take a essentially the same as r, but not exactly r. I will just put singleton elements in sets like this. Now elements of A are sets. These are singleton sets, but anyway, that's fine. And then I claim that the size of A and R are the same. Why? Because from R to A, I can have a map X going to set X, and this is a bijection. Fairly straightforward to see. Therefore, this set A and this set R are of the same size, that is, they are equinumerous, and by the power set theorem, so size of A is equal to the size of R, which is less than the size of 2 power R, which we have taken as set B. Happy? Okay, fine. So although there is a single countable infinity, there are many uncountable infinities. All these are collectively called uncountable. Okay, so in this course, we will not worry too much about, I would say, how uncountable an uncountable set is. Is it like R or 2 power R or 2 power 2 power R? But these are big mathematical questions, but well beyond the scope of this simple-minded, I would say, treatment. Moreover, we do not require for the moment this classification of uncountable infinities. Anyway, so second question is another interesting question. Suppose that A is an uncountable set. What you do from that uncountable set, whatever it is, it's like R or 2 power R or 2 power 2 power R, something like that, anything. Only thing, it is not countable, uncountable. This is uncountable. I just take out countably infinite number of elements from A. Okay. So, first question is A minus B, is it possible that this A minus B is countable? Let us first understand this. Is it possible that A minus B becomes countable?
No, sir.
Why?
Sir, because then A minus B union B will be the union of two countable sets, which is A, which cannot be uncountable.
Okay, good. So that is the appropriate answer. I'm not writing it. I hope everybody heard this. So the next question is, we have taken out certain elements from B. Still, can you establish some kind of bijection from A to A minus B or A minus B to A, whatever. Bijection is always invertible, so it's between A and A minus B. So that means, is A equinumerous with A minus B? So what kind of uncountable cardinality A has is not important. I am just asking the question whether A and A minus B are of the same size. It should be equal, I think, but this is not a question of thinking. You should establish it. Yeah, your intuition is correct. Yeah, C minus aleph naught is equal to C, that is true, but why? Better, I suggest better we do not worry too much. Yeah, aleph naught is too small. It is not aleph, A-L-E-P-H. Anyway, so let us not worry too much about this C, aleph naught, aleph 1, aleph 2, these terms. Let us try to use the standard notion of sets, functions, in order to establish this kind of arguments. Yeah, aleph naught is too small. The size of B is too small compared to A. So intuitively, it is clear that A should be of the same size as A minus B because you have taken essentially an insignificant part out of it. That is the intuition, definitely. I agree. You should be driven by some kind of intuition, and this is the correct intuition in our case. So, you still have to establish it mathematically. So, first of all, note that A minus B is a subset of A. And therefore, I have the natural inclusion map from this to this, A minus B to A. And therefore, I can say that this is true. So in view of the natural inclusion map. Okay. So to show that, I also have A sorry. Size of A is less than equal to size of A minus B. So to that effect, okay, to produce an injective map, let's call it F, from A to A minus B. Okay, so it is fine if F is bijective, but it need not be. If producing an injective map is easier in this case, propose an injective map, otherwise it's fine. If you can produce a bijective map, good. And actually you are not using this result. But it suffices to have an injective map from A to A minus B. Yeah, so how?
Sir? So can we extract another countably infinite subset of A, means something else?
Good.
And then we can map the elements which is like in B in A to that subset.
But then where will that? Okay, well, let's say that this set is C. So we'll map elements of B to C. But then where will we map the elements of C? It should be injective. Yeah. The idea is good.
To C.
To C. C to C, B to C.
Yes, sir. B union C. So if you do B union C to C, then
Union C. Yeah, please repeat once more.
so B union C to C, and then the rest is normally
Union C to C. Yeah, so that's a better idea. So you won't run out of elements from A minus B while mapping to A. No. This is not very precise argument. So from A. So A contains something called B. So this is my A, this is my B. So it contains B1, B2, B3. And we have seen that A minus B still remains uncountable. Whatever it is infinite. So I can scoop out another uncountable, sorry, another countable set C1, C2, C3 from A. Whatever remains is still uncountable, but that doesn't matter. So this A minus B does not have this thing, but it has this C1, this C set. Okay. B is not there. Now what I will do, this is an infinite number of elements, this is an infinite number of elements, countable although. So what I will do, I will map B1 to C1, C1 to C2, B2 to C3, C2 to C4, like this. And whatever else is there, it will map to itself. Okay, so formally, f from A to A minus B is defined as fx equal to if x is bi, then this is c 2i minus 1. If x is ci for some I, and this is c2i x otherwise. Okay. And you convince yourself that this F is not only an injective map, it is also a bijective map. This is actually a bijection.
Sir,
Tell.
shouldn't it be B to I minus 1 B to I because mapping is from A to A minus B? Then why are we considering C on the right side?
What is the question?
Means we are mapping B union C to C, right?
Yes. And the remaining things will go wherever it is.
We map B union C to B.
Yeah, so BI will go to CH2.
Oh, okay, understood.
B union C will go to C, not B.
Yes, B is not available in.
B is not there in it. Okay. So whatever your intuition is, try to establish it mathematically using some such constructions. Okay, but saying like Aleph not too small compared to C, these are all true, but this does not mathematically establish statements like this. Okay, so this is where I want to highlight the distinction between intuition and actual proofs. Of course, you will be driven by your intuitions, but formally establish things. Okay. Okay, I think this is fine. Okay. This is again another, I would say, tricky question. So the real interval 0,1, that is the set of all proper fractions. This is uncountable. We already know, right? Using the diagonalization argument. Some of the new queries actually raise some concern about diagonalization proofs, but I didn't really understand. Anyway, I will personally communicate with the person who sent this query. This real interval, and now just make a Cartesian product. So it is something like a two-dimensional space, and you have this square. So it's something like this. This set is like this, 1 by 1 square with this boundary excluded. And so this entire thing, and this first set is only this interval. But this is excluded. So they too are of the same size.
If element is x comma, means if a coordinate is x comma y, then we can map to x plus y by 2 on the interval 0 comma 1.
This is certainly not injective, right? For example, 0.1 plus 0.5 by 2 and 0.2 plus 0.4 by 2 will map to the same thing, right? So this is not injective. If we consider the set to be A with elements A0, A1, A2, we can map AI to A2, A2, A plus 1. No. First of all, note that this is an uncountable set. You cannot enumerate it like the way you did. You cannot enumerate.
Sir?
Yeah.
Sir, like all the elements in 0, 1 cross 0, 1 will be of type 0.A1, A2, A3 and so on, and 0.B1, B2, B3 and so on. Now what we can do is that we can take the fractional parts and concatenate one at the end of other in a fixed fashion, means second at the end of first, and then map it to the corresponding real value which is lies between 0 and 1. Then we can get an injective map.
There is only one small problem here. Okay, so I assume that you are talking about decimal expansions, of course.
Yes.
This is a natural thing we do, but you can take any other base. Let us talk about decimal expansions. The only problem is that some elements have two decimal expansions, like let's say 0.1. 0.1 is same as 0.099999. Okay. So, but if you look at this kind of bad things, you will find that these are essentially the rational numbers, right? So only rational numbers may have two different expansions. There is another suggestion, mapping x to square root x square root x. Okay, let me see. No, this is certainly not a bijection. Injective part is fine. Okay, actually you can map x to x comma x, y square root. Just map x to x comma x. No need to take square root at all. Okay. So for this exercise, let me first do this. Okay, but before going there, what I say that these elements may create some problem. Q intersection 0, 1. And let us call it set all rational fractions in the range 0 to 1, inclusive of 0, but exclusive of 1. What is the size of this set? The This Q is countable, right? And this is a subset of Q. So F is also countable. So if I take out a countable quantity from this uncountable set by the previous exercise, the size of this and the size of the original set, they are the same. Okay. Also, I can consider this, subtract from, sorry, this. This. F is countable, F cross F is also countable. Again, if I subtract or take out this countable set from this uncountable set, the set size does not change. Happy?
Yes, sir.
So I essentially, yeah, tell.
Before means doing why we are removing rational numbers, can you explain means what problem will they create? I did not.
Think of this 0.1 and 0.0999999. These two are essentially the same thing. Okay.
Yes, sir.
But I prefer to all the elements to have a unique decimal expansion.
So can't we choose some sort of convention that if it is having a terminating one, then
You
we
can do a lot of things, but you can do a lot of things, but maybe you have to be a little bit careful about arguing in that case. Okay.
Okay.
So first of all, so I will now establish or I would say, I will establish that this set and this set, they are of the same size. Okay, so one-way injective map from this to this. Simply take x going to anything, maybe like x comma x, or even x comma 0, or 0 comma x. Sorry. Or somebody suggested this, square root x, square root x. This is also fine. Okay. And so on. These are all injective maps. Okay. Again, there is a suggestion, one-way injective from A cross A to A, we can map. No. This multiplication is not injective. For example, 0.16 is 0.4 times 0.4 and also 0.2 times 0.8. But after taking F, will it happen? That's a difficult question. No, then also it's not true. Obviously not true. Okay. So for the converse, what I do, I take two elements. One of the form A1, A2, A3. B1, B2, B3. And I will simply map it to This is injective, right?
Yes, sir.
Okay. And you are done. The two-way injective map you have produced somehow, and you are done. So essentially, this example also illustrates the fact that sometimes it is easier to propose two-way injective maps in place of a bijection. So this is also perfectly fine according to the Cantor, Schroeder, Bernstein theorem. Okay, so this is an injection, this is another injection. Together they established we can have a bijection between this set and this set. Okay, so these are, I would say, a little bit new type of argument that you are facing now. This kind of mathematics perhaps you have never done. Okay, although you know injective maps, bijective maps, surjective maps, but the applications of this are quite profound, right? Okay, so fine. 8:47. I do not have enough time, so I think the first part is covered in some earlier tutorial. So define a relation on the set of real numbers. A and B are related if and only if they differ by a rational number. And prove that first. This is an equivalence relation. And this is, as far as I remember, this is done. But anyway, this is routine check. Okay.
Fill half of the cavity with.
What was the question? I didn't understand. Was there a question? I don't know. Anyway. So that this is an equivalence relation because a minus a is 0. 0 is definitely a rational number. If a minus b is a rational number, b minus a is also a rational number. And if a minus b is a rational number and b minus c is another rational number, then the sum a minus c is also a rational number. So this is routine check. So second question is, if I look at the set of all equivalence classes of this relation, is that set countable or not?
Sir, not countable.
Why?
Sir, we take representative of each equivalence class as fractional part of a real number which lies between 0 to 1, 0 closed, 1 open.
Like
Means if we take such a fraction between 0 and 1, then all those real numbers will be included in that equivalence class which have fractional part same as that of representative.
So for example, 0.5 is a fraction, proper fraction, right?
Yes, sir.
0.25 is also a proper fraction.
Yes, sir.
And their difference is 0.25, that is 1 by 4. So 0.5 and 0.25 are in the same equivalence class.
Oh, yes, that will create a problem.
So I mean,
all the rational numbers will be in same equivalence class, all the rationals.
yes.
And then all the irrationals will have their own equivalence classes, and we can prove that the number of irrational numbers is uncountable. Because the irrationals will have They're different classes. Root 2 and root 4. Not root 4, root 3 and so on.
I didn't hear the voice actually, did not come. So, okay. So first of all, R is the union of, or it's actually a disjoint union of the equivalence classes. Okay. So R is the union of the equivalence classes, and the number of equivalence classes is exactly the size of this set, R by tilde. So if the number of equivalence classes is countable, R is a countable union of certain sets. Okay. So suppose R by this is countable. Then this union is a countable union. And therefore, if each equivalence class is countable, R is a countable union of countable sets and is countable, which is a contradiction. Okay. So the question is each equivalence class countable? Okay, so if each equivalence class is countable, then R is a countable union of countable sets and is therefore countable. And this is a contradiction already, but we have not yet established this thing. If this can be established, then the initial assumption that R by this tilde is countable, this is false. So what about this?
All of them will be equanimous with the size of Q.
Yes, right. Okay, so this is actually true. Why? Consider the equivalence class of A. Or maybe I just do it opposite way. Let us define a map F from a rational number R will go to A plus R. First of all, is it a well-defined map? Because A and A minus R, sorry, A and A plus R differ by R. So the equivalence class of A and the equivalence class of A plus R are the same. In other words, A and A plus R are equivalent. Therefore, A plus R is a member of this equivalence class. So this is a well-defined map. Happy? Next. So first of all, F is well-defined. F is injective. Is it true? Is it true?
Yes, sir.
Obviously,
Yes.
right? If you take two different rational numbers, add them to A, you will get different elements. So this is obvious. Is F subjective?
Yes, sir.
Okay, just take anything equivalent to A. By definition, A and that thing will differ by a rational number. So if I take that rational number here, that will map to A plus that rational number, that thing. So this is also trivially true. So from Q, I can establish a bijection to each equivalence class. And therefore, each equivalence class has exactly the same size as Q, but Q is countable. Okay. That's all. Happy? Okay, maybe this is just a small question I ask. The set of all univariate polynomials with integer coefficients is countable. So do not, again, I would say, confuse polynomials with infinite power series expansions. Every polynomial has a degree, and all coefficients beyond that degree will be 0. Okay, a polynomial is not the same as infinite power series expansions. So any hint? Any suggestion?
Sir, for any polynomial of a particular degree, we only have a countably many polynomials, and since there are only countable many degrees possible, it's a countable union.
Okay, so that's the basic idea. So first of all, you take the zero polynomial. Its degree is typically taken as minus infinity, mathematically. Okay. So this is a single case, doesn't matter. So now fix a d greater than or equal to 0 and consider all polynomials of degree d. So they are of this form: a0 plus a1x plus a2x square ad x power d. Okay. Now, by the different choices of a0, a1, a2 up to ad, I will get different polynomials. Only thing, ad should be non-zero. So these are integer values. So there are countably many choices of a0. There are countably many choices of a1. There are countably many choices of a2. And this is only restriction is ad is not equal to 0. So still, just take one element out from the set of integers. It still remains countable. So countable possibility, countable possibility, countable possibility, blah, 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 up to ad. There are only countably many possibilities, and d is a finite quantity. Okay. So the size of this is basically a d plus 1 fold Cartesian product of countable sets. And therefore, this is also the total number of polynomials having degree exactly equal to d is countable. Okay. And now you take the union of over d polynomials of degree d. Or maybe this is set notation. Okay. So this will be my zx. Okay. But d varies from, okay, there is a single case minus infinity, and then you have 0, 1, 2, 3. So this is countably many possibilities. Therefore, zx is a countable union of countable sets. So this is countable. Okay. Okay, fine. I think we should stop here because it's already past 9 and I don't know whether you have another class now, which is very likely. Okay, so we will solve a few other countability and uncountability questions in the next Tuesday tutorial, I would say. Okay. Fine. So if you have any query, immediate query, let me know.
So why is the degree of zero polynomial taken to be minus infinity mathematically?
Okay. The justification of this is this. If you have a product of two polynomials, then the degree okay, it should happen like this. But if you multiply 0 with anything, you will get the 0 polynomial, and then you can see that the only number that satisfies number, I mean within quotes number, that satisfies this equality will be minus infinity.
Okay, sir, yeah, good.
Okay, and it should be less than 0, of course. Okay, so that's again, that's just a convention. Yeah.
Okay.
So in the question where we took that another set C and mapped B union C to C, so does that proof work if we take B such that there is no other like countable set remaining? Does that make sense?
Yeah, what did you say? This is a countable set, this is another countable set. So whatever.
So if we do something like there is no other countable set remaining in this, does it? Okay, no, sir, no.
I don't understand. Does size of R belong to n? No. Infinity is not a natural number. Even the size of n is not a member of n. Infinity is not a natural number. Infinity is not an integer. Infinity is not a real number. Infinity is not a complex number. Infinity is nothing. It's just a concept. It's not a number.
So in that case of zero polynomial, couldn't we take the degree to be like plus infinity? Still the condition would hold that degree of fg.
Mentioned that zero polynomial should have degree less than the degree of this and this and this.
Okay,
Yeah.
okay, sir. Okay.
Infinity is not a good choice.
Okay, sir.
So sir, it can work like this for degree for polynomial of degree n. The nth degree will have some non-zero coefficient, and from n+1 onwards it will have 0. So from that we can say minus infinity.
Yeah, that is the definition polynomials. But if you consider infinite expansion like a0 plus 1 x power d plus ad plus 1 x power d, this will never stop, then this is not called a polynomial. It is called a power series expansion. And in fact, that set, the set of all power series expansions within integer coefficients, turns out to be uncountable. Yeah.
So then can we say that the size of an infinite expansion is also uncountable?
Size of?
An infinite expansion.
Infinite. So it's good that you try it. The moment you go to infinite expansions, you will get uncountable infinity. Why? So propose some kind of argument. Maybe diagonalization is good here. Perfectly work. Okay, so any other question now? Okay, then I stop sharing first. And stop recording.